Okay.
Cyber warfare going on.
Yeah. We're going to start talking about making the airplane three-dimensional now. And when we do, things start to couple. We get roll with yaw and yaw with roll and those kinds of things. And they even at higher angles, we deal primarily with side slip rather than angle of attack. And when we get to rather high angles of side slip, even longitudinal couples a lot of times, and we have some strange motions of the airplane. However, airplanes were, unlike helicopters, were made to fly straight. And so what we, side slip, although we reference things to it, it's really not exactly like angle of attack in that respect, because angle of attack we need, it's a usable thing. Side slip, there's only one case where we really use it. So that's, there's some similarities and some differences, I guess is what I want to say. But the angle at the plane of symmetry, we cut the airplane in half down the middle. The angle that makes with the relative wind, which way the wind is blowing, most of the time it's right on the nose. But when it gets from the side, one or the other, it's side slip. And that angle between the relative wind and the plane of symmetry is the side slip. Wind blowing from the right. If you're in an open cockpit biplane, when the wind's on the right side of your face, you've got positive side slip. And when the wind's on the left side of your face, you've got negative side slip. That's how we define it. Okay. Now, the angle that the plane of symmetry makes with some fixed reference is called the yaw angle. The only time that these things are actually the same, there's probably one case if we say, okay, true north is our plan, our reference. Then if we were flying true north, then side slip and yaw angle would be of the same magnitude, but of equal opposite signs. So yaw is positive when the nose is moved to the right. Okay, we said wind blowing from the right was positive side slip. Well, when the nose moves to the right, it's positive yaw angle from that reference. And a lot of times we just say, okay, our initial heading is the reference. And so if the nose moves to the right, that's positive yaw angle. Side slip, well, we can loosely compare it to angle of attack, while yaw can somewhat be compared to the pitch angle. But like I say, the only time these things are the same but of equal opposite sign is in a wind tunnel. I used to teach a lot of wind tunnel guys when I was in Tennessee, because we had the Air Force Arnold Center wind tunnel complex right next door. And they had a hard time understanding a lot of things. For instance, they had a hard time understanding the phugoid. Because with the phugoid, you got big changes of pitch, right? But the angle of attack doesn't change. And in a wind tunnel, hey, if you've got so much pitch, it and the angle of attack are about the same. And so they used to be amazed that, we go through all these big oscillations, and one of the airplanes we had a very unstable phugoid motion. And, but if, I had somebody looking at the angle, we had an angle attack gauge on that airplane, somebody looking at the angle attack, and of course during this whole oscillation, the angle attack stayed the same. But the pitch angle was making big changes, They had a hard time with that. Well, when we have side slip, we generate not only a yawing moment, but a rowing moment too. Okay, so lateral directional is coupled motion. We will see when we look at the lateral directional equations, we will see not only yawing moments, but we'll see rowing moments and that sort of thing. While angle of attack has a lot of use, side slip has little use except in crosswind landings. The only time when side slip is useful is in generating a side force to counteract drift. When you're landing on a, you're landing on a runway and the wind's blowing like this, and so you put one wing down into the wind. When you do that, the airplane's going to want to turn, right? So you have to put in opposite rudder, cross-controlling, so to speak, to keep the airplane going straight. Well, what's going on? The wind's blowing from this way. We're generating a side force to counteract the wind. Now, what's neat is if you have direct side force control. And when I was at Tennessee, I had an airplane that was called a Navion, which had big surfaces that stood out about midway on the wing. And you could deflect those surfaces. And so you could land wings level with those surfaces deflected, generating direct side force control, because when you move those surfaces, the rudder also moved, and you would just, you would generate so much force. So I would come in and I'd line up on the runway, and I'd reach for the direct side force control, and I'd dial in whatever stopped the drift. And then I could go ahead and land the airplane wings level without having to put a wing down. I land on both main gear, not one main wheel as you do in a normal crosswind with a conventional airplane. It was neat. We probably should do it on particularly transport airplanes. There's some cases with a big airplane like a 747 or a 777 where if the crosswind is strong enough, you can't really land without dragging an engine on the ground. Or you end up trying to turn into the wind and touch down and hope you can get it straight once you get the wheels on the ground. Not so good, But if you had direct side force control, hey, you can land normally. Having that airplane was a lot of fun, and using some of those features was quite good. It made a crosswind landing real easy. It was like a landing with no wind. Well, since side slip is a factor in both lateral and directional stability, such stability is measured in a steady-headed side slip. And in a steady-headed side slip, the acceleration terms in the equation of motion are zero. Since we don't have any, steady heading, so we're not translating. So the acceleration terms are zero. And these are the three equations. We have a rolling moment equation, a yawing moment equation, and a side force. Now, if you'll think back to when we talked about longitudinal, we had two force equations, right, and one moment equation. Here, we've got two moment equations and one force equation. And notice that each of these equations have both, that's delta R, that's rudder deflection, that's aileron deflection. So they have both lateral and directional components. We didn't have that with longitudinal. So you can see that this stuff is coupled. These motions about these axes are coupled. Side force, this is lift coefficient and bank angle in this equation, okay? So that's the side force. You tilt the lift vector. You know, all of a sudden the lift vector is pointing this way and not straight up. The first term in the yaw moment equation is the side slip term. Go back to that. Oop, went the wrong way. Notice that this is the side slip term. That's side slip, side slip, side slip. This is side force with side slip, side force with rudder deflection, side force with aileron deflection. Okay. Lift coefficient times bank angle. Yawing moment coefficient times side slip. Rowing moment times side slip. So all of these have coefficients with from each, both lateral and directional. Directional stability, we always like to, if we can, to combine things. And so one of the things I like to do is take my airplane, turn it 90 degrees. Now, all of a sudden you can see, other than the wing, airplane looks pretty much like it did in longitudinal, right? So what's going to contribute to directional here? What's going to be the big contributor? Right off the top of your head, going back to longitudinal when it was a horizontal tail, right? The rudder and vertical tail. It's going to be the big contributor to directional stability. Fuselage doesn't matter whether it's like this or like this, it's destabilizing, okay? You know, if you took the tail off and what have you, and flew the fuselage, it'd eventually go end over end. You know, I mean, the Goodyear blimp even has to have a tail. So, like longitudinal stability, directional stability is the result of contributions of the components of the airplane. Only the wing, which now is like so, differs, and we'll talk about it. Tail is a primary contributor, we've already said that, and when placed to the side slip, the vertical tail generates a side force, and that derivative, the non-dimensional derivative, is cy beta of the vertical tail, or the side force due to side slip of the vertical. So here it is. Notice that that's the lift curve slope of the vertical tail, okay? Thinking back to when we looked at longitudinal, that equation looks like 1 minus d sigma d beta, or the change in side wash, d sigma, with side slip. Now remember on longitudinal it was d epsilon d alpha, right? Change in downwash with angle attack. Thing of it is, the downwash doesn't affect the vertical tail that much, okay? So this is a rather small term. Tail efficiency factor. However, you put a T-tail on top of the vertical, it makes the vertical tail more effective due to the in-plane. You know, if you put a T-tail up here, it's like having an in-plate on a wing. Okay. Area of the vertical over area of the wing. Okay. And of course, this guy is dynamic pressure at the vertical over the free stream dynamic pressure. Again, that's someplace due to everything's in front of it. It's again about 0.9. maybe a little bit bigger with the T-tail. The yawing moment, so the side force creates a yawing moment, creates a moment about the center of gravity. Okay? So Cn beta, that's the yawing moment, Cn beta of the vertical tail is Cy, or the side force coefficient of the vertical tail, times the length of the vertical tail over the wing span. Remember, we in longitudinal we used the mean aerodynamic chord, right? Here we use the wing span. And of course, the length is the distance of the vertical tail from the center of gravity back to the CG. And from that equation, the tail's contribution is a function of the tail arm, the lift curve slope of the vertical tail, and the vertical tail area. Now, if you go to a reference like Perkins and Hage, Stability and Control, good old book. Everybody in this business ought to have one in his library. Okay. You can actually, he's got ways of calculating many of these coefficients in there. Well, by the time the airplane gets to the flight test program, we're not likely going to change the tail arm. We aren't going to make the tail longer. Right? You know, too big of a change. However, we can modify the lift curve slope of the vertical tail. And there are a couple of ways of doing that. The dorsal fin, okay, a fin in front of the vertical. That increases both the area of the vertical tail and it reduces its aspect ratio. What happens when we reduce the aspect ratio of a aerodynamic surface? What happens to its lift curve slope? Anybody recall?
Does the coefficient of lift increase for slower plates?
No, what happens is the lift curve slope decreases, but it extends way out there, so you go to a much higher angle of attack before it stalls. Okay? A very high aspect ratio wing, for instance, has a very steep lift curve slope, but a fairly low stall angle of attack. Where if you have a small aspect ratio wing, the lift curve slope is reduced, but it defining the stall and the angle of attack goes way out there. So what's this going to do to the stall angle of attack of the vertical tail? Stall angle of attack is going to get higher if you use this. Now, what's this going to do though, and what will this do to the center of pressure? It's going to reduce it, right? It's going to come down. It's not going to be as high up. We put this on here. The center of pressure, may start out up here someplace. We put this on there, and center of pressure is going to move down here. So what will that do for the roll-yaw coupling? It's going to reduce it, right? It's going to reduce the stall angle of attack. Increase the stall angle of attack, which is good on multi-engine airplanes. One of the things we worry about in the flight test business is a thing called rudder lock. And we'll talk more about that in a bit. But what happens is the rudder, as you get higher and higher side slip with the rudder, next thing you know, it goes zoom, and there it stays. And here you are in this horrendous side slip, and of course, due to being You know, the airplane doesn't have much drag going this way. It has a lot of drag going this way. Okay, so what's going to happen if you get into rudder lock? You're going to be coming down because you may not have enough power to stay up there. And particularly, it usually occurs, rudder lock will usually occur in a single engine situation on a multi-engine airplane. Ooh, you already can't have much performance because those of you who are in the performance course know that if you lose one engine on a multi-engine airplane, how much performance do you lose? It's a lot more than half, isn't it? So you don't want to get into a rudder lock situation in that case, and of course you're going to need to hold a lot of rudder, you know, as they say in the multi-engine training, dead foot, dead engine. Okay? Whichever, to keep the airplane straight, whichever foot you're not working real hard is the one that, that's the dead engine side, okay? And your good engine, if you've got your right foot in there, it's the right engine that's running, it's the left one that's dead. That's how you, initial thing as to how you quickly identify which engine failed. You have an engine failure. So this would be a good fix then for rudder lock. Again, going to the airport, see multi-engine airplanes, look and see if they have a dorsal fin. They do, and particularly if it's fairly big, you will know in the flight test program they probably had a rudder lock situation that they needed to fix. Again, you know, when I see a new airplane on the ramp that I've never seen before, I like to walk around it and look for things like this. Okay. It tells you right off the bat how good a job the designers did initially. Okay. Tells you right off the bat. Because when you see all the flight test fixes, you know that they didn't do a very good job to start with. And so the flight test guys had to fix it. Well, ventral fin. Ventral fin is put on the bottom. Yes?
Rudder line, how does that act like actually happen? This isn't just a mechanical system.
It's a mechanical system, but what happens is that the vertical fin stalls. And when it does, the rudder floats.
Oh, and it just...
Yeah, and so it gets real happy there too, you know. It can be on a big airplane, it can be of such, require so much force to center the rudder up that the pilot is not strong enough. Well, the ventral fin increases the aspect ratio of the vertical tail. And it moves the center of pressure down even farther. You'll see ventral fins on a lot of jet airplanes. Because they will tend to have very bad Dutch roll characteristics in many cases. And so one of the fixes for Dutch roll or a lateral directional oscillation, and that lateral directional oscillation is kind of like a phugoid, except it generally has a shorter period, so it happens faster, and the pilot has a more difficulty trying to control it. About the best thing you can do is just try to stand both feet on the rudders and hope to help damp it out, because you don't want the rudder floating with it. But anyway, one of the solutions is to put a ventral fin on. T-tail airplanes generally need ventral fins for that reason, because you put the tail up on top of the T-tail, that moves the center of pressure up. makes the airplane more rolly. And where a rolly airplane gets into trouble is flying an instrument, a precision instrument approach. Because you're trying to keep you're trying to keep the needles in the right place. And when you got a rolly airplane, you tend to get in, if you try to damp it with pedal motion, a lot of times it'll just make it worse. You'll get in the loop with it. Well, again, these are handy gimmicks to be used to fix problems during flight test programs. Easy to do. There's something you stick on the airplane, as opposed to making a big change to it. Well, the wing contribution directional stability is small. Sweeping the wings improves the contribution, but it still is small. Generally, swept wing airplanes will have problems with Dutch roll. Again, because of the fact that the wing is sweep. When it's this way, the angle of attack is a little higher. It's going to tend to make it roll. Swing back the other way. Now, angle of attack is higher. It tends to make it roll the other way. So things get worse with each oscillation. Fuselage in the cells for directional stability are destabilizing as they are longitudinally. And again, putting the engines aft or pusher propellers help that. They make it less or make it more stable. So they're similar to longitudinal cases. Freeing the rudder, so the rudder is free to float, reduces directional stability just like it does longitudinal stability. High Mach numbers reduce directional stability due to the reduction in the vertical tail lift curve slope with increasing Mach number. The other thing that happens is if you plot lift curve slope, we'll call this lift curve slope here, and versus Mach, and Mach increasing. This goes in, let's say this is Mach 1. It goes along here like this, and then it does this number, and then it does this number. And out here about Mach 2, it's about half of what it is here. Sorry. So, with the lift curve slope going down out here at high speed, you may wonder why Russian airplanes and U.S. airplanes that are high speed all kind of look alike. Most of them had two vertical tails. That's the reason right there. Years ago, when I was in the Air Force Reserves, we used to get so-called intelligence briefings. Now there's, some folks say that the term military intelligence is an oxymoron. Okay? But anyway, we used to get these intelligence briefings, and they would always come in, these intelligence officers would always come in and tell us, here's the Russian such and such, and it's obvious that they copied the F-15 or whatever airplane it was. They didn't copy it. That drove them to doing the same thing. When you get to very high speeds, airplanes come out looking alike. Can't help it if you make them stable and what have you. But, it was always, they've copied this and copied that. And if you really found out the truth, folks in the Soviet Union grew up in a completely different world and did things in many cases completely different. For instance, when I was working on my doctorate in Germany, I had a friend who was the chief civilian at the German Forces Flight Test Center in Manchester. And of course, when the wall fell, they got, a lot of these Russian airplanes. It was very interesting to, for instance, I sat in the cockpit of an Su-22, which was a swing wing airplane, somewhat akin to the US F-111. But it was completely different. I mean, the cockpit and the instruments and the controls were completely different. For instance, it was a swing wing airplane, and the big lever over here on the side, I thought, well, that must swing the wings. Now, a little switch up on the glare shield was what swung the wings. I mean, it was, we wouldn't have done that thing this way on this side of the Atlantic, but like I say, they grew up in an enclosed, different world, and they saw things different. At the time that I was there, their Mach compensator device, and this has been several years ago, I'm sure they figured it out by now, but they had an aerodynamic compensator for the airspeed indicator to take care of Mach number. The folks in Germany hadn't figured it out yet how it worked, but they said it worked really great. We do it all electronically on this side of the Atlantic, So that's the interesting sort of thing. I mean, a lot of the aerodynamics makes airplanes look alike, particularly high-speed airplanes. Minor contributions to directional stability are provided by ailerons and spoilers. Ailerons, when we deflect them, generally today we deflect the one on the downgoing wing up more than we deflect the one on the upgoing wing down. That kind of reduces what we call adverse yaw. If you deflect them both the same amount, what will happen? You deflect the aileron, say you're going to make a right turn. Well, you deflect them both the same, the nose will go left first before the roll catches on and brings it around. Good example airplane of that is the de Havilland Otter, single engine Otter. It has big 40-degree Fowler flaps, and the ailerons, when you put the flaps down to 40 degrees, the ailerons droop 20 degrees. That airplane, if you just set it and try to rock from one wing to the other, the nose will get really wild. You think it's going to depart controlled flight if you don't coordinate the rudder really well when you make a turn. So, ailerons produce adverse yaw, while spoilers are stabilizing because they produce proverse yaw. Spoilers, come up on just one wing. So if you're going to make a right turn, the right spoiler would come up, spoil the lift, and essentially add drag to the downgoing wing and overcome any additional lift or induced drag on the upgoing wing. So they produce proverse yaw. And get the opportunity to fly an airplane with spoilers, I encourage you to do that. Well, lateral stability, we talked about directional stability. We said we could look at it like the longitudinal. Lateral stability really is not a stability in the true sense. Lateral stability comes about due to dihedral effect. Again, it's classified as positive, negative, or neutral based upon how the airplane rolls when subjected to a side slip. A roll away from the direction of side slip is considered positive. So if the side slip's coming from the right and the airplane rolls to the left, that's positive lateral stability. Okay? Normally we only want lateral stability to be slightly positive, since excessive roll with side slip complicates a lot of flying tasks. You really don't want a lot of lateral stability. In fact, you can get by without any. Now, the FAA regs require that you have some. but you don't want too much. Wing is a primary contributor to lateral stability through dihedral. And we'll take a look at that. That's the dihedral angle. And the wing into the side slip will have an increased angle of attack. So you can kind of see that here. In this case, the side slip's coming from this direction. This has a higher angle of attack than it does on this wing, and so it tends to roll away. Positive lateral stability. Sweep of the wing also considers or creates favorable rolling moments. Here we go. Notice higher angle of attack on this wing than on this wing due to the sweep. As a result, many swept wing airplanes will actually put a little bit of what we might say is negative dihedral, or sometimes called anhedral, in order to keep this, and particularly if they have a T-tail, which will give you a fair amount of roll with side slip. For instance, the F-104. F-104 was essentially an engine with a couple of small wings and a T-tail, T-vertical tail. The wings weren't a lot bigger than this table. This way. I mean, its wingspan was 21 feet, I believe. The wings were a symmetrical, high-speed airfoil. That the leading and trailing edges were so sharp that when the airplane was in the hangar, they put things on the leading and trailing edge to keep the mechanics from hurting themselves by walking into it. That's how sharp they were. Had a big, tall T-tail, had a couple of ventral fins, and it had negative dihedral in order to keep the roll down with the side slip, even though it was a straight wing airplane. Well, I've already mentioned that last bullet there, so we'll move on. Location of the wing on the fuselage is a major contributor to lateral stability. High wings are stabilizing, and low wings are destabilizing. And Cessna has always beat the drum on this because they have high wing airplanes. Generally, a high wing airplane like a Cessna can get by with 1 or 2 or 3 degrees of dihedral maximum. Our Cherokee 6, on the other hand, has between 6 and 7 degrees of dihedral due to the fact of the wing location. And you can kind of see what's going on here with the flow of the wing, or flow of the relative wind, depending on the side slip. The other, on the right side, shows what happens with rudder deflection with tail locations. You don't see many airplanes with tails on the bottom like that bottom chart, but that's what. Propeller slipstream also affects lateral stability because during a side slip, the slipstream from tractor engines go over the wing away from the wind, producing an unfavorable rolling moment. And that moment is increased when the flaps are deflected. So we say we have the flap deflected here. The slipstream is going over the wing. That means this wing is going to have more lift. Notice the side slip from the right, we would like the right wing to pick up, but due to the fact that this one has more lift due to side slip, particularly if the flaps are down, it's going to tend to roll into the side slip rather than away from it. We will look at this on the Cherokee 6 when we fly, and you'll see that low-wing airplanes have a hard time passing the FARs regarding lateral stability because of that. Because you can get to essentially a full rudder side slip, and for a steady heading, you may not have more than 5 degrees of bank, and the rule says you should have 10. Well, 10 was based on Cessnas. Okay, high-wing airplanes will have it. See, back in the old days, Dwayne Wallace, who was the president of Cessna built so many airplanes, he had a lot of clout with the FAA. And so some of the rules got written to benefit Cessna, and the other companies just were stuck living with them, okay, because of that fact. So unfortunately, politics, and if you've been watching the politics here lately, you've been scratching your head like I have. Politics have a lot of influence, whether we like it or not. Well, a lot of parts of the airplane generate a side force, but the main contributors are the vertical tail and the inclination of the lift vector. So we got the lift vector going up here, and we bank the airplane, and all of a sudden we got a side force going that way, just due to the lift vector. Well, that causes a lateral translation in the side slip, which is useful in crosswind landings. We talked about earlier. The crosswind landing, we put the wing down into the wind, camp that lift vector, and so we, if we took a piece of air at the time we did that, we're actually moving this way. Although, the fact that the wind's blowing at that velocity, we stay straight. It's dependent upon bank angle due to the inclination, and that makes a plot of bank angle versus side slip, an important factor in determining side force. And if you remember back to the equations I had on the board, that term was in the equations for a steady heading side slip. Okay, control free. What we've been talking about so far has been hold the controls fixed. What if we let them go like we did on longitudinal? Well, as in other forms, control-free lateral directional stability is expressed in control force. And for an irreversible system, the equations look essentially the same as they did for longitudinal. And you might expect as much. For a reversible control system, these forces are a function of controlled surface float again. And for a lateral control system, the float is small and the control forces are also small. The rudder, on the other hand, has a large floating tendency. And the float angle of the rudder can be expressed as delta R float, or the float angle, is equal to the hinge moment due to side slip of the vertical tail over the hinge moment due to rudder deflection times the side slip at the vertical tail. And the force resulting from that float can be expressed with this equation. Well, if you'll recall, that equation looks a lot like the force for a reversible system longitudinal, right? Notice that we've got an equilibrium position here and the float angle. And, a few of these other terms. K is the control system gearing constant in radians per foot. Dynamic pressure of the vertical tail, Q, pounds per square foot. Rudder area, and MAC of the rudder in feet. And if we differentiate that equation, the other equation looks like this. And notice again that if these two guys are equal, what happens to the rudder force goes to 0. That's the condition for rudder lock. Force equals 0, and that condition is called rudder lock. And one method to fix a problem with rudder lock is dorsal fin. Well, here's the kind of data you will get. Now, one of the things I want you to notice here, you know, most of what we've been doing so far, longitudinally, a lot of the stuff has been reasonably linear. Very little in lateral directional is linear, which is one of the reasons that trying to model this mathematically, you know, if you're using the equations of motion, not real great, okay? I mean, you know, there's folks out there who think they can model an airplane. Once had a guy who'd spent a lot of time trying to do that worked out at NASA Ames Research Center, who spoke in one of my short courses, and he had this comment, which I thought was a real interesting comment. He says, "Only God knows the math model of an airplane." Okay? A lot of truth in that, because notice this stuff isn't linear. It's only linear over very small deflections. As soon as you yaw this airplane, or as soon as you side slip this airplane enough to start seeing these things, what's going to happen? You're going to get separated flow from some part of the airplane. And when that happens, linearity goes out the window. And so 2 or 3 degrees of side slip is about all you can expect to have linear equations. Beyond that, they may become very nonlinear. Actually, this one here, which was taken on a wire, really looks pretty good compared to some I've seen. Some, I mean, you know, they go completely nuts. So be careful, I guess, is one of the things I'm trying to get across to you here, is be careful about mathematically modeling, particularly this stuff, at anything beyond a few degrees of side slip or what have you. You're just fooling yourself that the answer you're getting makes sense. So, with that said, you know, I think we'll be in the flight test business a long time. But this is the kind of thing you can get. This is rudder force here, okay, and this is side slip. So you plot everything, you know, and of course you go left and right. This is rudder force. This is rudder deflection, okay, versus side slip. Again, rudder deflection versus side slip. Bank angle versus side slip. Aileron force versus side slip. These are the kinds of plots you get from a lateral directional test, and that's as far as you can take it. You can't go to reduce neutral points and any of that stuff. You end up with this kind of a curve, and like I say, the equations of motion are only going to apply over a very small range. Before you start seeing separation from various places on the airplane. Questions?